G'day, I'm Rob Welke from Adelaide, South Australia. I'm an independent consultant in the irrigation and water supply industry and operate throughout the world. I've been actively working since 1968. That's 52 years, but never sold product. My passion is testing equipment. So you could say I've had a pressure gauge in one hand and a flow meter in the other. I've used these unique experiences to put together the Pumping System Masterclass. So sit back and relax over the next 26 minutes as I take you through the salient features of this class. It comes with software packages, which we'll have a look at as we go. And one of the big issues, it considers limits of operation of all irrigation components. And that's something that is terribly important when we consider selecting pumping and irrigation components. Like I say, I've been to the US 8 times since 1998, and I've also been to 3 conferences where I've presented papers on energy efficiency. First time in Seattle in 2017, and Long Beach, California, where I met Chris Wickman there, and then last year in Vegas. What are my background? I have an associate diploma in mechanical engineering. I'm a certified irrigation agronomist, a certified irrigation auditor, landscape, and I have a certificate for training and assessment. I'm also HACCP certified, which is Hazard Analysis Critical Control Point for recycled water. I did a lot of recycled water in Queensland a few years back. And I live in Adelaide, South Australia. Well, there's Adelaide, South Australia. It's the driest state of the driest continent in the world. We get most of our water from the River Murray, which in turn drains from the Murray-Darling catchment in the eastern states of Australia. In a dry year, Adelaide gets 90% of its water from the River Murray because it's so dry in our state. I was fortunate enough in the very early 70s to be attached to the pumping engineer of South Australia's Water Supply Authority. And that took me on a remarkable journey of testing and monitoring the energy efficiency of pumping plant and pipeline infrastructure throughout the whole state. And because it's dry, there's a massive amount of pumping infrastructure here. And so it's the knowledge from this background that I brought to the irrigation industry that makes my presentation so different from everybody else's. Over the next several decades, I got out, I left the water supply company after 25 years and then got into the irrigation industry. And I went out doing, as a consultant, doing audits and designs. So I got to see the best and the worst of the industry. And it was the worst of the industry that prompted me to write these training courses. And one of the things I found in particular was the irrigation industry was so focused on the pump as far as energy efficiency. So if you want to do a pumping energy efficiency audit, you test the pump. And in reality, if you want to do a pumping system energy efficiency audit, you test every component of the irrigation system, apply a head loss, measure a head loss, and then compare with best practice. Well, they say best practice, but what is best practice? Often it's what the manufacturer might tell us. So, you know, we have to be a bit more critical of what is best practice. And that's one of the things that I look at in the training course. So if we look at, you know, the components of where energy can be saved in an irrigation system, we have, you know, pump and motor efficiency over here, which is so heavily focused on in the industry. What I focus on more is the irrigation system itself, and look at the total head pumped and divide it up, and then look at where we can optimize and save energy. And principally, it's in mains and sub-mains and lay flat hoses, pipe aging, pump suction, valves and filters. And because we can't see them, we often refer to that as the elephant in the room. So what component, when we look at energy savings, well, if we just look at the pump and assess the energy efficiency of a system, we could be typically only looking at less than 50% of recoverable energy losses. The rest is in the hydraulics. And this course really concentrates on the energy recovery from poor hydraulic systems. As part of the system, it is based on a model of 200 acre-feet. So if, for example, a golf course, 200 acre-feet, a center pivot of 200 acre-feet, and there may be drip irrigation systems. And this enables people who attend the class to identify with a size of irrigation system. So they can say, oh yeah, well, you know, you're talking about so many dollars lost here for a 200 acre-feet irrigation system. Mine's 400 acre-feet, so I've got twice the losses, you know, so it's a system of comparison. The course looks at energy for irrigation, looks at pipelines and optimization, pump suctions and NPSH, pump selection, filtration, and pump station design and pump testing. And pump testing is a fairly strong one, lots of traps in pump testing. One of the significant parts of the course is with software, and I'm going to deviate from here. This is the main software pump data calculator. So I'll bring this up here. This takes the formula for calculating energy from the NRCS book. Well, that's exactly the same that I use for metric, just a slightly different conversion factor. So it's a constant times the total dynamic head times the cost of electricity times the volume divided by pump efficiency, motor efficiency, and drive efficiency. And that finishes up in an annual cost from there. And that in turn goes through an amortization process where we amortize that annual cost over 15, 20, or 25 years. You know, I was doing a bit of a calculation here yesterday for a major potato grower in South Australia. And in addition to that, we look at carbon emissions, now probably on a regular day-to-day basis. That won't come into your vocabulary, but if you're looking at government schemes, they will almost invariably require you to assess the carbon emissions and carbon emission savings if you're doing any design or auditing work. So this takes information from AVERT, which is a government website, a federal government website in the US, and they're the zones, they're the energy zones that the US are divided into, and so they're represented here. And so they calculate the ton of CO2 per year that an irrigation system will generate. It has a diesel component. So there's a diesel. If you're pumping diesel, you can calculate the energy cost for a diesel, and that's quite accurately done. It takes the principal measurement from the engine manufacturer, which will specify the brake specific fuel consumption of a diesel in either, you can drop down either grams per kilowatt hour or pounds per horsepower hour. You can divide both of the electric and diesel systems. You can have a choice of acre inches, acre feet, 100 cubic feet, cubic meters, milling gallons as your input for the volume pumped per year. It's got a breakdown of all the energy costs in cents per kilowatt hour throughout the whole of the United States, and that's been one of the guides that I've had to assess. Okay, so we'll get back to presentation. So using this calculator, we can come up with things like kilowatt hours per acre feet, and we can look at how much 1 foot of total dynamic head costs you over 25 years. And I've divided this into California and the rest of the country. California has the dubious honor of having the most expensive energy in the country, almost by twice as much as all the other states. So I've divided it up in that respect, and that's a fascinating insight into how much it's costing you to operate any one single device in your irrigation system. pipelines, we look at a whole heap of things, some pretty introductory level stuff, and then we get into calculating friction and hydraulic optimization, measuring friction in the field. It's an incredibly interesting activity, measuring friction and deriving the Hazen and Williams C factor. One of the things we do is look at a Hazen-Williams equation versus a Darcy-Weisbach. Now, Hazen-Williams gives us a C factor that's often used in our irrigation industry. The Darcy-Weisbach is used, and the Manning's formula similarly is used more in industry, and they refer to the condition of a pipe in terms of its internal roughness. So what I've done is combine the two and come up with a comparison. And so, you know, we can tell, you know, a Hazen and Williams factor. So just as an example, 0.004 of an inch bore roughness inside of a 3-inch pipe will reduce the Hazen and Williams C value from 150 to 130. Now you can't even see 0.004 of an inch, you know, and how does that get there? It gets there from biofilm, from unchlorinated water sources such as rivers, dams, and recycled water, and that's all we pump with. Well, what about glacial rivers? There's glacial flour in glacial rivers, silt from rivers and dams, loss of zinc from galvanized pipe, iron hydroxide, and salt precipitation. You've probably seen them all. Hydraulic optimization. What's the optimum size of a pipe? As the pipe diameter goes up, the cost of laying a pipe goes up. But as you do that, the pipe friction goes down as the pipe diameter goes up, and the energy costs go down. So where's the sweet spot? Well, we look at the sweet spot. We look at how to find the sweet spot. In fact, I've got an app just for that. And let's just look at that app briefly. I'll pull that app up, and we've got Hydrops here. So this is the apps. We have a series of input data, including supply and lay costs, and we can input data here. So 0.12 315 125 Hazen Williams feet, pipeline length of 3,000 feet, 1,300 gallons a minute, and a pump efficiency of 0.75, and motor efficiency of 0.93. And these are all input factors. And from that, it calculates the optimum diameter in inches over various various pipe ages. So for 25-year life, the optimum diameter for those set of inputs is 10.83 inside diameter. If you want to have a look at how that works, in fact, it refers to a graph in the back office where each of those ages is defined by a curve representing the change in capital cost versus the diameter of the pipe, and then it references the actual cost of supply and lay. Where those curves intersect, that's the value that we use. So that's Hydrops. We'll just minimize him. We look at pipeline pigging. That's a pretty important part. If you get into areas where you have silt, we can actually, now I don't think you've got sound on that, by the way. I forgot to activate the sound. So here's another pipeline pigging exercise where we cited an instance of what was otherwise very clean water going to a lateral move, and we decided to pig the pipeline, and that's what we got out of it. Everybody was shocked. So there's all sorts of surprises when we start delving into the inside of pipelines. Center pivots, you know, there's lots of stories to be told about how they degrade in time, and you know what a mild form of galvanized a loss of galvanizing can do to a center pivot. We cover that as well. So as far as limits of operation of a pipeline, we need to, start to define, well, if pipelines can be so variable, we need to take into account the system curves when we design a pumping system. And that's just an example of the limits of operation taken into account. We'll see that a little bit more later. In NPSH, yeah, this is probably a bit more standard, but I've got an excellent graphical indication of how net positive suction head works. We look at minimum submergence, suction screening, and screen area calculator, and lots of case studies. And this is the calculator for MPSH and MPSH pump, MPSH calculator here. So this is the MPSH required curve for a pump, and there's the feet and head. Normal maximum is 33.9 feet. So we can put some figures in. I'll just show you how this works. We got, if the best efficiency point is 1100 gallons a minute, the irrigation duty is 1300. We're going to maximum flow 1425 and a Hazen Williams value of 150, and that brings up a red line which defines the maximum NPSH available, which is 33.9 feet. Then we go through and we add a few figures, like we've got 3 feet of positive head, so that takes the NPSH available up 3 feet. Then we've got atmospheric pressure, that's 30.8, and so that brings it down because we're elevated. We got vapor pressure, 1 foot of vapor pressure brings it down. We got 1.5 feet of margin, that brings it down even again. Then we look at the suction pipe, so we might have 100 feet of 9-inch pipe, so we start to get an inverse exponential graph. Then we got fittings losses, 0.8, and the last thing is velocity head correction, and this is the killer often. If we've got a 5-inch inlet flange, so that now defines the net positive suction head available, the red line, and where that red line crosses the blue line, that's the limit of operation. This course is about limits of operation, and this enables you to see graphically. So you can program this for any pump you like, and it's a fascinating and valuable piece of gear. Then we get into pump selection. We'll look at some introductory stuff, and then go into one of the things is limits of duty of a pump. We got the upper and lower limits of duty defined by the hydraulics, and that goes back to what we saw in the pipeline section. Where pressure sustaining valves, if there's any item in an irrigation system that sucks energy more than anything else, it's a pressure sustaining valve. We'll look at that. We'll look at pump guarantee limits for pumps. You go back to your HI 14.6 for this. Pump materials in construction, we look at corrosion. Then we look at electric motors and VSDs, and in terms of efficiency. Then we do some typical pump selections, single flow, multiple flows, and multiple flows and heads. And then we've got an app, I'll show you in a moment. All the curves and all the demonstration graphics are in gallons a minute, US gallons a minute, and feet head. I'll just say, this is what we're taught generally in the irrigation industry. This is what we're taught. There's a system curve for a pump, and here's the duty. The vertical line is the duty, and where they intersect, we've got to select a pump with the best efficiency. Okay, what in reality happens is that we've got multiple system curves considering our limits of operation, and when we go to select the pump, we've actually got multiple. We've got quite a wide band considering the pump testing tolerances from HI 14.6, and those tolerances are the same worldwide. All pump standards are the same worldwide. Plus or minus 9% flow, plus or minus 7% head. And when so your pump selection goes from a single point to a very large area. How do you control that? This course deals with that. And then we go into the pump selection, pump duty selection. So this is the one here. So we've selected some system curves, a range of system curves here for a particular center pivot selection. And here's the pump. We've selected a pump duty with a little bit higher head, and we can manipulate this. So up here we've got the pump impeller diameter, and by selecting a lower pump diameter, lower impeller diameter, we can massage this to suit our requirements. So it might be 11.7, I don't know. So so we've got to aim for this point here. That's the ultimate worst case duty of that pumping system. It's interesting to note that the pump duty will require to be operate over this range in the life of it. So, we might consider a VSD. And the other thing we can do in place of the RPM, we can put the 3000, sorry, we go 1750 and 1700. So because the affinity laws for an impeller are the same for the impeller diameter as the impeller speed, we can also substitute RPM into those figures. We can manipulate the shape of these curves. Instead of a C value of 125, we might have a really worse scenario, case scenario of a C value of 100, or we can lift the system curve to account for other factors, whatever we want. It's an extremely versatile little bit of software. And here's the motor, the actual horsepower that the pump requires down here in the green line. So that's the pump selection. I use that so often. It's just so powerful. Then we look at pump stations, a whole heap of things like power supplies, solar, the buildings, buoyancy, pipe work, electrical, occupation, health and safety, particularly ladders and documentation. Then we go into filtration, and this is not about filtration. This is the cost of filtration. Okay, the energy costs. And we look at ultimately at a case study where after an audit I identified $9,000 per annum worth of electricity savings from reconfiguring how the filtration system was installed. And that amounted to $166,000 over 15 years. That was for a large almond grower. And I found out 4 years later that all these other farms along the River Murray had been changed in similarly. We'll look at that, how that was changed. Pump testing, we get back to the HI 14.6. We look at pump testing formula, how to measure head, what not to do, what sort of gauges to use. Then we're measuring flow. Flow, I always used to say the accuracy of pump testing is 90% measuring flow. If you don't get your flow right, you're wasting your time. So we look at flow meters and their accuracy, and there's some pretty ordinary flow meters out there. How to measure power. We look at the theory and then the practice, and then pump operating costs. And then we go into a pump testing app, and I'll just bring this one up briefly for you here. So no, it's not that one. It's pump testing app down here. So it's got all the input. So you input your manufacturer's curve in there, and that may be a works test curve, or it may just be a catalog curve, in which case it's subject to ±7 and ±9%. So you've got to be really careful when you go to site. You'll probably never ever replicate the manufacturer's pump curve in a site test, and we'll learn why. Okay. So that's a brief expose of the software, most of the software. So how will this course help you? Well, for a start, the software is extremely empowering. It puts you in charge, and for designers, it enables you to design energy efficient irrigation systems and not just select energy efficient pumps. So it does the whole deal. For auditors, an essential companion for auditors. If you do any auditing of irrigation systems, these software are amazing. For what about farm managers? To evaluate your farm energy efficiency and verify it, rectify it. Potentially save thousands of dollars in annual pumping costs and tens of thousands amortized costs. You can build on your existing qualifications. At the moment, this course is presently with Irrigation Association for an IA Select ruling. And one of the best things is you can justify a position with your client. If you're going to deliver a product selection for your client, you can justify it, what you've selected by bringing up this software on your computer and say, well, if you do this and this and this, is going to cost you heaps extra, and that's probably what your opposition has done. Feedback, the amount of feedback we've got from this course is just mind-boggling. There's yours, Jim, at the top. Jim attended this course back in May, though that was the metric course. Excellent experience. I highly recommend it if you're involved in irrigation pumps. One of the things most stand out is the engineers. Engineers I think they have a very textbook view of how pumping systems work. This course just floors them. It totally changes the way they see pumps. Here's another one from Dowden's Pumping, Mackay. They employ 200 people, and I did an in-house course, and the staff come back the next day still talking about the course, and that they reckon is unique. People don't talk about courses, but this one they did. So there's a lot of indicators, out there. The most amazing thing is that all of those people who said this is the best thing we've ever seen are the people who've been in the industry 35 years and reckon they know it, and this has knocked them off their chair. So this course is powerful. There's no doubt about that. It has 6 sessions total. Each session's 2 to 2.5 hours. We commence at this point in time, 4 p.m. Pacific Daylight Time. That's 8:30 in my morning, so it's a bit hard to get up, start much earlier than that for me. And 3 days a week for 2 weeks. What do you get for your money? You get for each session, you get a set of slides with the notes covering all the notes. You get a tutorial, and the tutorial demonstrates how the software works. So without the tutorial, these software apps are of no value to you. Okay, and in this particular case, we've got a couple of bonus software apps. One's called iPeat, one's called Pipe Suite. So here's iPeat. It stands for Irrigation Pumping Energy Efficiency Assessment Tool, and I'm going to bring this up because this iPeat Pro, iPeat US. This particular bit of software I designed after considering dozens and dozens of field audits, and I put together a software that will predict the energy efficiency of your total system without even going to site. So if you just have a few things, first of all, it's what type of irrigation system is it? Whether it's a center pivot, lateral move, or a big gun, or a knocker rotor, or a drip spray, flood, transfer, pipe and riser. And each of those types of irrigation system has a unique hydraulic footprint. And you go to any of those that are similar, and they are very similar. And so I've been able to create algorithms for each of those that predict, given the residual pressure at the end of the system, the feet and elevation, the amount of water pumped per year, the kilowatt hours consumed, and the electricity cost. And this is one particular one. This was the one that where the really dirty water was coming out of the pigging exercise. The potential electricity savings on that particular scheme was 56%. So that was more than half. So this guy had the potential to more than half his electricity costs. And we did actually do that on that particular scheme. Okay, so that's a very powerful piece of kit. And there is, I'll just minimize that. How do I get, I can take that over there. I can go here. There's a video you can watch when you receive this video. There's a that's one of the first videos I made, going back a few years. So we'll just leave that one alone. That video is on my website.